On this computer. Hope everybody's had a good weekend, safe, healthy, all that sort of stuff. And welcome to week 2. And today we're going to be talking about the uncertainty principle. And let's start this up. Any questions from last time before I get started? And I do want to remind you, there's no homework due this week, but there are 2 worksheets that are due this week. The worksheet from Friday that we talked about, and that is the statistical interpretation tutorial. Okay, that tutorial will be due Wednesday, end of business day. And then today, we're going to be talking about the uncertainty principle. There's a tutorial on that as well, and that'll be due Friday of this week. So no homework, but your homework is to complete the 2 worksheets. I normally do office hours at 12:30 on Mondays. I'm going to slide that back a half hour to 1 o'clock. And it'll be a mixed office hours for both of you and my 112 class. I don't expect they'll have too many questions. You all may be the more likely person to come and ask questions, probably about the worksheet from last Friday. Okay, and so that's the plan for the week. Let's get on to talk about I have one other thing before I get started. I've been using just a very rudimentary whiteboard, and it's okay. Jacob found me a resource that he said some of his other professors are using. It's an online web-based whiteboard. It's called awwapp.com. And I found that to be a little bit better. I can't get it to screen mirror right now, so I can't seem to call it up, but I don't think I'll need it today. But that might be good if you come to office hours and you have a question for me, because it does give you the ability to collaborate. We share a link, kind of like you would for a YouTube video, and then we can both write on the whiteboard at the same time. For those of you who are just answering the tutorials on a blank piece of paper, you may find this cuts out a step for you, because if you have one of these cool little pens here with the rubber tip, you can write, and a tablet of some sort, you can write right on the tablet, and it becomes a PDF. You can save it that way. And then you don't need to take a picture of it before you upload it into Canvas. So that might be useful as well. A good resource that we might need moving forward the days ahead. All right, anyway, back to uncertainty principle. And cue up my little pen here. And remember, we had the uncertainty principle from modern physics, and I know I certainly talked about this. We talked about the uncertainty in momentum, and the uncertainty in position had to be greater than or equal to Planck's constant divided by 2, and the uncertainty in energy times the uncertainty in time also had to be greater than h bar over 2. Hopefully you left modern physics with that understanding. I'll call it the Heisenberg's uncertainty principle. Today we're going to generalize that out. Because the uncertainty principle does not just apply to position and momentum and energy and time. It actually applies to virtually any observable we can make on a quantum mechanical system. And we also found way back in chapter 1 that this delta that we used in modern physics is a little bit imprecise. We specifically talked about a standard deviation in momentum and a standard deviation in position, as opposed to just some kind of vague uncertainty. So not just position, momentum, energy, time, and also this delta we've refined to be a statistical quantity called standard deviation, the square root of the variance. And we'll remind you what all that meant here in just a second. But I want to start off with determinate states and the eigenvalue equation, like we've been talking about. And remember that the eigenvalue equation is this. Well, first of all, it works for the shorter wave equation. The time independent version is a eigenvalue equation, but anytime mathematically you take an operator on some state function, an eigenfunction, and that could just be a mathematical function, okay, like a polynomial. It could be a vector where every component of the vector is a mathematical function, or it could be a vector where every component of the vector is just a number, generally a complex number. But in any event, you operate with some operator, and so far we've seen Hamiltonians, positions, and momentums, right? Those are our three choices to date. You operate on that function. When you get back a constant times the exact same wave function, you have an eigenvalue equation, and that's what we see very often in quantum mechanical systems. And if that's true for that particular function, you can see the function is what causes this to happen, not the operator. If that's true, then we say that the expectation value must be solved this way. Remember, this is an integral equation. That means the integral of psi star, psi with the operator operating on the psi times dx over some space where this thing applies has to be equal to, I guess, this, okay? And that, because of the energy eigenvalue, or because of the eigenvalue equation, whether it's energy or momentum or position, and because this is a constant, I can bring it outside the integral. And then, of course, for orthonormal states, that is just one. That inner product of psi star psi is just one. And that leaves me the eigenvalue as the expectation value for that operator. Remember what an expectation value is. If I had 100 identically prepared quantum mechanical systems, maybe 100 atoms, and I was looking at the electron in each one, and I made a measurement of whatever this parameter is, position, momentum, energy, and I made that measurement, the expectation value is the average of those 100 measurements. Okay, now in this particular case, because it sure looks like, since this operator and this state are linked together, okay, when I find the expectation value of the operator squared, that just means I do this operation twice. I do it the first time I bring out a q, I do it the second time I bring out q squared, and then I'm of course left with psi star psi, which is orthonormal, it's just one, I get q squared. For this particular case where this wave function is just matched up perfectly with the operator, you see that the uncertainty, well, q squared minus q squared is 0. And we call that a determinant state. And a couple of people have asked me in office hours, well, what do I mean by a determinant state? I went scrambling back because I was on a little bit of a loss for words. One of the smartest guys I ever met as a professor taught me quantum mechanics in grad school the second time. And when he talked about this, he referred to a determinant state as sort of a preferred state for whatever it is that you're measuring. Preferred in the sense that when you operate on that state, you get a constant back times the state. And that gives it a special status. The status, of course, is that any other state that the system could be in is just a superposition of linear combinations of that state, of those states, I guess I should say. And so that gives it special status for that particular observable and that particular operator. Okay, anyway, that's what we're talking about here. For any observable, there's a set of states that are determinate, preferred for that observable, and these are eigenstates of the Hermitian operator associated with that observable. Because remember, anything we say we can observe has to have an associated Hermitian operator. And that's key to everything we're going to talk about. If these operators weren't Hermitian, a lot of this mathematics that we're doing in the formalism chapter here, chapter 3, wouldn't be true. Okay, we couldn't make the math work. Determinant states of total energy, in addition to being called determinate, are referred to as being stationary, but we don't, and they're not changing, I guess. We don't say that about states for other observables like momentum, position, angular momentum, z component of angular momentum, anything else we're going to talk about moving further, unless they also happen, those states also happen to be determinate for the Hamiltonian, for the energy operator. And we'll discuss an example of that. When are they? When does an operator have the same eigenfunctions, eigenstates as the Hamiltonian, as the energy operator? There are some cases, and you've actually seen it. You just may not have remembered it in modern physics. All right. Anyway, I got to go back way to chapter 1 to when we talked about variance and standard deviation prior to talking about the uncertainty principle way back then, because we're going to review that, and then we're going to generalize out to what it really means. And so we said a variance in general is just some observable. And the reason I'm summing here is, remember I said we could make this measurement 100 times, so I might be summing making a measurement of J 100 times. I compare it to the average value of J. So I guess this is something I do in post-processing. I have to figure out what the average value of J is. And then I go through with each of the values, I subtract the average and I square it, multiply by some sort of weighting factor, and that gives me the variance in that parameter J. And so I guess that's how we started, and we got it back to another rule that I think we've used multiple times on worksheets and homeworks. But remember, if I want to square that thing, okay, inside the sum, I would square the parameter that I measured, okay? And you might want to, if I want to put an index on the sum, maybe I make this n and I'm summing over n here. So this is n and I'm summing over n. But because I'm lazy, I dropped all this, okay? Any event, if I square this, that means I square that guy. I square that guy, and there's positive. And then, of course, the cross term is minus twice. I guess that would be subscripted again, the observable times the average value of the observable J. Okay, and so that's just squaring out this thing. Again, multiplying by this, this probability function that you have that varies with J. And I think math says I can write this now. I got three terms. I can write it as three different sums. So I can sum the first term times the probability function. I can take the second term, the expectation value squared, times the sum of the probabilities. And then the last term I got is minus 2 times the expectation value times the sum of J times the probability. And realize an expectation value is just a number. It's the eigenvalue. It could be a complex number, but it's just a number. Okay, on the worksheet, the tutorial we did on, I guess it was called Dirac notation, the very last problem where you had to take a matrix and a row vector and a column vector and multiply them out to get a expectation value for that operator, even though it was a vectors that had numbers on them. When you were all done, you got a number. It happened to be 47, if you remember. Some of you incorrectly, and hopefully you looked at my notes, made the answer for the expectation value be I guess in your case, everybody who did it, there were about 3 or 4 of you, you were left with a column vector when you were done with that. And that's because you weren't properly multiplying a row vector times a column vector, a little bit of linear algebra problem. But conceptually, you got to realize this is just a number, okay? Like in that particular problem, it was 47, right? So that gives me the ability to bring it outside the sum whenever I see it. Okay, and so that's why these two are brought out. All right, now we've come as we moved along in the course to have some idea of what this means for a quantum mechanical system. Okay, that sum there, really we turn into an integral. The probability function is psi star psi, there we go, psi squared, if you want magnitude of psi squared. And then we put the function that we're weighting with that probability function in the integral, and we integrate it between some range, and that's what we're talking about for this expectation value. So that's all I've got right there. And I guess this guy right here, that sum, well, hopefully you realize the sum of all the probabilities has to go to 1, right? And let's see, this guy, well, that would be similar to this, only it would be J squared times the probability. And so I guess that would be that guy, which I'm calling just the expectation value of J squared. And so that went to 1, so I brought that over there. And this guy just was the expectation value of J. That's why it became 2 times J expectation value, J expectation value. And if you look, that's just J expectation value squared. So those two terms right here can be combined together. And so we've got the expectation value of J squared that came from this term. Okay, and then these two terms give us J squared minus 2J squared, where J I'm talking about is the expectation value of J squared. And so of course I get the expectation value of J squared minus the expectation value of J quantity squared, and that's the variance. To get the standard deviation, we take the square root of both sides. And that's why we've been using this rule over and over and over again to figure out what the uncertainty in a particular measured quantity would be for a quantum mechanical system. And of course, if you've got the eigenfunction that's associated, that's preferred, that's determinant for this this operator and the expectation value, then that uncertainty is going to turn out to be 0. All right, so great. let's back it up then. We're not going to use this one. We're going to go back to this original guy right here, which did define what a variance was. It is, question out there?
Just as tall as white kids.
Gabrielle, I'm gonna have to, don't make me mute you. You got a question?
Oh, right. Sorry.
Nope, no worries. Just wanted, just so something was coming through. In any event, we're gonna use the original definition of the variance, okay, from statistics, which is the value of the thing. You subtract it off from the average value of the thing, and then you square it. Of course, these pointy brackets here mean that weighting function. You're nesting this thing in psi and integrating over. In our case, we're only doing one-dimensional problems so far, always integrating over x. Okay, and so I guess because we're working with an expectation value and the right set of eigenfunctions, we'll say that the expectation value is just the eigenvalue, and I'm substituting that in right there for the expectation value. That quantity, that difference is squared. Okay, that means this is written twice. So I can get rid of the squared, and I would go Q minus the eigenvalue times Q minus the eigenvalue. And then you see what I did? I took one of them and I slapped it from where it was up here when this was squared, and it's not anymore. And I brought it over to the leading, the bracket. I brought it over here. And the argument for the ability to do that is, remember we said all these operators have to be Hermitian. Simply subtracting a constant from a Hermitian operator doesn't change the fact that it's Hermitian, so I can still bring it out here and not change anything, okay? So this is sort of our bottom line definition now of what the variance in any quantity we can measure in a quantum mechanical system. And admittedly to date, position, momentum, energy, that's what we got, okay? So that's why I'm writing, oh, there it is. My cursor, there it is. That's why I'm writing this. So that's what I'm going to do for variance. Okay, so the uncertainty principle deals with the uncertainty in two quantities. Uncertainty is the square root of variance. And so I need the two quantities then. I'm going to call them A and B for lack of better names. Okay, and just where I had Q minus the expectation value of Q, Q operator minus expectation value of Q, I'm changing it to A right here. And then of course I got another one, B. And we're going to define this thing right here to be F. And you can see this variance is just the inner product of F with itself, where this is what I mean by F from what I just said about how to get a variance from a statistical point of view. And of course, the uncertainty in B would just be G, inner product with itself, where G is the same thing, but for the operator B. Now, something we did before the break, we talked about an inequality in linear algebra called the Schwartz inequality. I said we'd be using it again. Here's the time. The Schwartz inequality says that the inner product of a vector multiplied by the inner product of another vector, do I have this right? Yeah, it has to be greater than the inner product of the other two vectors squared. And yes, I do have this right. I was worried I had my equal sign, my greater than or equal to sign backwards. If you think about this, think about like a dot product. If I had the vectors F and G, right, that would be the magnitude of vector F, and I suppose I should put vector symbols on them, but I said it and I just didn't write it, times the magnitude of the vector G, and times the trig function for the dot product. It's the cosine of the angle in between them. Okay, and so I guess the question is, which is bigger, these two things or this thing? And the answer is that the two magnitudes multiplied together has to be bigger, because this is a number that is less than or equal to 1. The biggest the cosine can be is 1. But in general, it'll be like 0.5 for 60 degrees, you know, things like that, square root of 3/2, numbers like that, less than 1. And so this piece right here has to be bigger than this piece right here. And so if I squared them all, Well, that still has to be true. This has to be, these two things squared have to be bigger than that, okay? And that's why I'm saying that is just the magnitude squared of F. This is the magnitude squared of G. And of course, this is the dot product squared. The two magnitudes multiplied together have to be bigger. And that's the Schwarz inequality, okay? Now look, we said that F inner product with itself and G inner product with itself were the variance in A and the variance in B. And so apparently the variance in A and the variance in the B have to be greater than the vector F inner product with itself squared, okay, according to the Schwarz inequality. Moving on here. I got to do a complex number review here because we're going to do something with what I just said here in a second. And in general, a complex number can be expressed as a real and a complex part, an imaginary part. I sometimes like to refer to the imaginary part as complex. That's a misnomer. The imaginary part turns a number into being complex. But in any event, X is the real part of this complex number Z, Y is the imaginary part of the complex number Z. Okay, and so if I ever want to find the magnitude of the vector Z, and we've done this multiple times, you take Z and you multiply by its complex conjugate. So I take this guy right here, and I multiply it by its complex conjugate formed by making the square root of -1, the I term negative. And what that does is it always eliminates the cross term, right? I get X squared and I get Y squared, minus cancels that minus sign right there, and that's why it's plus. The cross term, the 2xiy, well, it's plus 2xiy minus 2xiy, they cancel, and so that's the answer. Okay, sure looks to me from this that the magnitude of the vector Z squared is X squared, the real part of Z squared, plus the imaginary part of Z squared, and that always has to be bigger than just the imaginary part squared. The only time it could be equal, hopefully you can see if the real part of Z, if X here happens to be 0, they'd be equal, but because they're positive numbers, you're squaring them, okay? The real part plus the imaginary part squared has to be greater than the imaginary part squared. And that sort of just makes sense. As long as real Z is got a value, a non-zero value, this will always be true. Okay, and you can see how the Schwarz inequality introduces a greater than. Here's another case where we've got a greater than situation. This stuff over here has to be greater than that. Now, how do I manufacture the imaginary part of the complex number Z? Okay, in terms of Z, right? That's what I want. I want the imaginary part of Z in terms of itself. And what I did is I just looked at Z and its complex conjugate here, and I subtracted the two. So Z minus the complex conjugate, X minus X is of course 0, and IY minus a minus IY is a plus 2IY. And remember, Y is just the imaginary part of Z. So I substituted that in. If I solve for it, all I have to do is divide through by 2I, bring it to the other side of the equation. And the imaginary part of a complex number is always 1 over 2I times the complex number minus its complex conjugate. That's kind of a rule, and I've just proven it, I suppose. So that's the imaginary part. And so now if you come back over to here, when we had this inequality, the magnitude of a complex number squared has to be greater than its imaginary part squared. Complex number magnitude squared has to be greater than its imaginary part squared. It's exactly equal if there is no real part, if the real part is 0. But in any other case, this has to be true. I'm just going to substitute that right in there. And so the magnitude of a complex number squared has to be greater than this thing. And that's the complex number minus its complex conjugate. Divide that thing by 2I and square it. That must be true. Okay, so let's put this all together now. We were left, due to the Schwarz inequality, that the variance in A times the variance in B had to be greater than F inner product G squared, magnitude squared. And we just showed that the magnitude of any complex number squared has to be greater than its imaginary part squared. And so let's let Z be that inner product of the two functions f and g. Let's not lose sight of what those two functions were. those two functions were the things, I guess it almost looks like the square root of a variance for two different operators, right? So that's what we were using here, okay? And so I guess if Z is going to be determined to be that, then I put it in right there, and I put it in right there with a complex conjugate. And so we're getting close to the generalized uncertainty principle here. The inner product of those two functions, f and g squared, must be greater than 1 over 2i times the difference between f inner product with g minus f inner product with g complex conjugate, because we've defined z to be that inner product. All right, complex conjugate allows me to flip the order of these two things and eliminate the complex conjugate. That was a linear algebra rule we've looked at before, and so that's what I have right here. Okay, again, the variance of the observables A and B have to be, the product of those things have to be greater than all of this stuff. Let's bring it on to the next page, and let's figure out what is that inner product of f and g from these two functions that I put a square box around before. Great. Okay, let's see. We said f and g then would be this written on the bra side, okay, and then this on the ket side. And notice what I've done is I brought this right in there and put them both on the ket side, preserving the order. But what allows me to bring that into there is that the operator A, like every other operator associated with a quantum mechanical observable, has to be Hermitian. Hermitian gives you license to bring that piece right there and slap it right in there without changing anything. So now both functions, f and g, are on the ket side, and then I'm just going to multiply them out using the distributive property, preserving order when necessary. And when necessary is in this term right here. It's A times B as operators. Now these two guys, the expectation value of A and B, they're just numbers. So when I get to those terms, I have the ability to flip their order around, right? It doesn't matter whether I write A operator times a number, or the number times A operator. In this case, it doesn't matter. I chose to write the operator first in both cases, but it really is irrelevant because these are just numbers. Of course, these are both numbers, so I could have written expectation value of A or expectation value of B in either order. Point here, though, is this is all inside the psi star psi integral. And so I can write it as 4 different integrals, right? 4 different integrals. The first one has operator AB. This one has the expectation value brought outside, but then you notice that guy right there is just the expectation value of A. Did the same thing for the next term here, where B was still inside, and I brought the A expectation value constant outside the integral, but you recognize that is just expectation value of B. And then, of course, that thing right there, psi star psi, that's just 1 for an orthonormal basis set. And so these 3 terms right here really are exactly the same. Order isn't important here because these are just numbers, but that one's negative, that one's negative, that one's positive. And so apparently the inner product of f and g, where f and g were these 2 operations, okay, these two functions, well, f inner product with g would just be the expectation value of the product of AB in that order minus the expectation value of A times the expectation value of B, because that's what you get from these 3 things. On the other hand, and you remember there was the reverse order of these 2 things, that would just be B times A minus the product of those 2 things. And the reason I'm doing that is because we were left off with F times G minus G times F. That's where we left off on the product of the 2 variances. Okay, so let's just make that subtraction, because we're going to need to substitute it in here. We're going to take this guy and subtract off that guy. And I think that's what I did here. There's FG, there's GF. Hopefully you notice those 2 cancel. And then FG minus GF is just the expectation value of the product of 2 operators, the difference in the product of the 2 operators, okay, but reversing the order. And we defined back in chapter 2 when you have two operators subtracted from each other where the order is reversed, we refer to it as the commutator of those two operators. Remember, the commutator represents the degree to which two mathematical operations don't commute. If you were doing, say, multiplication and division, it wouldn't matter whether you did multiplication first, then division, and then division, multiplication. They're exactly commutative, we say. And so the order doesn't matter. You'll get the same number here, in which case the commutator would be 0. The commutator is 0 when two mathematical operations commute with each other. This commutator operator is a degree to which they don't commute. The difference between those two isn't 0. That's what a commutator represents. Okay, we're moving along here then. Generalized uncertainty. We just said that that guy right there is equal to the commutator of AB. Okay, it was an expectation value of the commutator for AB. So the generalized uncertainty relationship is that the variance of one parameter times the variance of the other parameter must be greater than all of this, which is the expectation value of the commutator of the two operators whose variances you've got on the other side. That's the generalized uncertainty principle. It's got a nice Washington College maroon box sitting around it. It's something that, you know, is an important enough equation that it would show up on an equation sheet. And it's true for any two operators. And let's look at 2 of the 3 that we've used. And a long time ago, we showed that the commutator of position and momentum was just IH bar. If you don't remember that, I called it the canonical commutator operation. It was the CCR that day. And if your parents trained you well in music from the 70s, you realize that's the Creedence Clearwater Revival operator, but that just helps me remember it. It's the canonical commutation relationship for momentum and position. It was IH bar. Okay, so what are we going to do? We're going to look at the variance in position and momentum, and we're going to substitute IH bar right in there. Notice the I's cancel, and you get something that we talked about at the very start, the uncertainty, because I took the square root, not the variance anymore. The uncertainty in position and the uncertainty in momentum must be greater than H bar over 2. Exactly what you'd expect. In modern physics, we would have written that as delta X, delta P is greater, delta P is greater than H bar over 2. And in quantum mechanics, we're being very specific about what we mean about this uncertainty. We mean the standard deviation. No kidding, the standard deviation, as we've defined from chapter 1. All right, some general comments here. And then we're going to look at energy and time, because that's the other one we have to consider. Position and momentum are an example of an uncertainty principle. Every pair of observables that you can think of that do not commute have an uncertainty principle. We focus on position and momentum because they just make sense, but energy, time are coming. You know, you could have angular momentum and position. I don't know. You can just kind of think about all the various combinations. Frankly, I haven't studied them, and I'm not an expert in them. Non-commuting observables, observables whose operators do not commute, are referred to as incompatible observables. In the laboratory, they cannot be observed simultaneously. And now how does nature ensure that's true? I mean, I've got a nice mathematical rule, but we talked about this both in modern physics and way back at the start of this course in chapter 1. If you have to do a position measurement, what we've said you're going to do to the wave function is you're going to collapse it down to just a spike at the measurement you make, okay? And then the question, of course, is what's the wavelength of that spike? Because the momentum is equal to h bar k, which is equal to h bar, let's see, k is 2 pi over lambda. And so if you pin down lambda really well, I'm sorry, if you pin down the position real well, you've got no idea what the wavelength is, in which case you have no idea what the momentum is. On the other hand, if you made a measurement of momentum, that would mean you've made a real good measurement of what the wavelength is. In order to make a good measurement of the wavelength, you got to have a number of oscillations. And now tell me, what's the position? Okay, where is the thing located? The position uncertainty becomes huge in this case because you knew the wavelength and you knew the momentum. That's how nature ensures that these two observables, position and momentum, are incompatible. Okay, and that's how it works. Incompatible observables do not have shared eigenvalues. Okay, sometimes people in the worksheet, the tutorial that you've got, will introduce the word complementary. Okay, there's even a multiple choice question dealing with this. I prefer the word incompatible with doesn't commute. It's the negative is both. And you notice this is not a negative when you say they're complementary observables. Incompatible does not commute. And then in that case, there's no eigenfunction of position, as an example, that's also an eigenfunction of momentum. Last week when we talked about the statistical interpretation, we had to create, by doing a differential equation, the eigenfunctions of momentum. We kind of waved our hands around for what the eigenvalues of position, the eigenfunctions of position were, and you notice they were two separate math functions, and you couldn't use one for the other. Compatible observables, okay, those are observables whose operators do commute, that when you do the commutator, you get zero. They have complete sets of eigenfunctions which are the same, okay? The eigenfunctions are determinant for both observables. And you may recall from modern physics, the hydrogen atom eigenfunctions, those were associated Legendre polynomials, Laguerre polynomials, all those things. Once we developed the hydrogen atom eigenfunctions, we used them for energy, we used them for angular momentum, we used them for the z component of angular momentum. Apparently those are compatible observables. The commutator of the operator associated with those observables must have commuted, and measuring one property like energy did not have any effect on the measurement of angular momentum, for example, because there was no collapsing of wave functions or anything like that. Okay, so those observables, angular momentum, z component of angular momentum, what it's hard to say, and energy, they have the same eigenfunction. We didn't even blanch at all when we did that in modern physics, when we made that conclusion, when we jumped to that conclusion, because we hadn't really thought about what are the eigenvalues of momentum and position, which are incompatible, which don't commute and have an uncertainty principle. There is no energy angular momentum uncertainty principle, right? It just doesn't exist because those are compatible observables. Their commutator is zero. Just as a quick proof on this, it's actually problem 316. I'm not going to sign it or anything like that, but simultaneous eigenfunctions for two observables must be compatible, which means they have zero commutator. Well, let's just do that. And I look at some of the tutorial notation. I could have made these eigenfunctions as kets, right? But I've got two operators with the same eigenfunction, f sub n here, okay? P and Q are the two observables, the two operators which have corresponding observables. The eigenvalue for P we're going to call lambda. The eigenvalue for Q we're going to call mu. Okay, great. And we're going to have the same function f, if you want to write it like we're often seeing in the Dirac notation, you can write it like that. It's a common eigenfunction for both the operators and the corresponding observables. That would be like energy and angular momentum, for example, okay? We're saying that this function f has some Fourier coefficients. It could be a linear combination of these functions. And so what we're checking is what is the commutator of these two operators, P and Q, operating on f. Okay, so commutator, remember, is the first times the second operator minus the second times the first. If they commute, that difference will be zero. Okay, and I'm putting the function right in here. And you can see the process we do is we have this guy operate on this guy. And once I do, if I have Q operating on this guy, Q operating on this guy brings out that eigenfunction right there, eigenvalue right there. My apologies. And then if I have Q operating on P, well, I've done P first. So when P operates on the function, it brings out the lambda. And so that's why that was written. Q and P operations are still yet to be done. You do them one at a time. Okay, so now I've got this sum right here where I've done the first operation. I've done Q in the first term and I've done P in the second term. And now I got to do P to the first term and Q to the second term. And when I do this operation, these guys are just constants. I operate P on F and I get the eigenvalue lambda in there. And when I operate Q on F, I get the eigenvalue, I guess, mu right there. And because these eigenfunctions were compatible, well, I guess were simultaneous. The eigenfunctions were simultaneously good for both operators. You notice these two terms are the same. You subtract them and you get 0. Okay. Remember what we started though, is we were doing the commutator of these two things. We've just found that the commutator had to be equal to 0 if we started off with the assumption that the eigenvalues were common for the two operators. Okay, the eigenvalues are common. It just turned out you had to have 0 commutator. And so we say they're compatible. Okay, any questions on that before I go on? Just kind of makes sense. All right, and one of the things, and I'm not going to go through all the math on this. You can read section 352 to actually solve the differential equation. But the question might be, and you've seen it a couple times in the homework, when is the product of the two uncertainties not greater than or equal to h bar over 2, but exactly equal to h bar over 2. And if you look at, there are two places where there was an inequality, right? One of them was the Schwarz inequality. And I guess this would be an equal sign in the case where G and F are proportional to each other. If G and F are proportional to each other, there's just a constant right here, which could be brought outside of one of them, and it would also be brought outside the other. And so these two would be exactly equal. Now, nobody's saying whether that constant is a real number or a complex number, has both a real and imaginary part. It's just a number. If they're proportional, then it wouldn't be greater than or equal to right here in the Schwarz inequality. It would be equal to each other. Similarly, we looked at the magnitude of a complex number, and we said it's always greater than its imaginary part, squaring both. Okay, and that would be an equal sign in the case where the real part was actually equal to 0. Then it wouldn't be an inequality anymore, it'd be an equality. Section 3.2 shows these conditions result in a differential equation. When you solve those differential equations, you got a Gaussian function. Now, when did we find a Gaussian wave function in chapter 2? And the answer is, I think, twice: in the ground state of the harmonic oscillator and a Gaussian wave package for a free particle. And so I tell you to, hey, go take a look at homework problem number 2 in the set number 4. Okay. And pretty much all of you realized, yeah, there was a time dependent product of uncertainty in X and uncertainty in P, but at a particular time T equal to 0, that Gaussian wave function did give exactly h bar over 2, not greater than h bar over 2 for that product. And so we've seen this once before, and sure enough, we were working with a Gaussian when we saw that special case, and so that kind of makes this all come together now. It's part of a general principle, generalized uncertainty principle, not just specifically those two, momentum and position. All right, we got to talk about energy and time here in a couple minutes I got left. I want to make sure everybody realizes time's different than momentum, than position, than energy. It's an independent variable. It's a parameter that moves forward in a quantum mechanical world. We're not thinking about general relativity or special relativity where it's actually a coordinate. We're thinking of it as an independent variable in our quantum mechanics. We're not doing relativistic quantum mechanics in this course. Okay, so time's an independent variable, and unlike the other ones, the other quantities, energy, momentum, and position, it's not the standard deviation of a collection of measurements, right? We said if you wanted to get the uncertainty in, say, momentum, you would make 100 measurements of momentum on 100 individually but identically prepared states, and then average and find the standard deviation to get that uncertainty. For time, that's not what we mean when we talk about the uncertainty in time. Instead, it's the time it takes a system to change, I'm going to use the word substantially right now, okay, by a significant amount, and we'll talk about exactly what that means when we investigate this, okay? And so because we're talking about an uncertainty in time, we got to consider an operator's expectation value changing in time. And so what's the rate of change of an expectation value of a particular operator? Remember, that's what it would mean. And this integral is in our shorthand Dirac notation expressed that way. Okay, so that's what we're going to start off investigating. And we're going to apply a product rule. Product rule says if I got to take a derivative on these three things multiplied together, well, I take the derivative of the first times the other two, plus the derivative of the middle things times the other two, plus the derivative of the third thing times the other two, and I preserve the order all the way through. And then, of course, the question is, what's that guy and what's that guy? Okay, because we can probably work through the other stuff, but those two are problematic. Not really. If we go back to the equation in chapter 1 that we really haven't used that often, the time-dependent Schrodinger's wave equation, the one that has the capital psi and includes the time derivative, okay, we saw that it was IH bar times this derivative is equal to this, and we've recast, I guess, this and all of this, we're calling that the Hamiltonian operator, okay? So if we're looking for the derivative of the wave function with respect to time, I guess we just take the Hamiltonian operator, the energy operator on psi, because that's this side of Schrodinger's time-dependent wave equation, and just divide it through by IH bar, right? And so that's gonna go right there and right there, and that's what I'm writing out here. Now, a couple things you might notice about that, because I'm still trying to do this derivative, and I got this product rule here. Okay, why is this sign negative? I just want to remind you that I'm substituting in right there, but it's on the left pointing, the bra side. Remember, this is complex. And so when I bring the constant out front outside this integral, because that is an integral, I have to remember that I've already taken the complex conjugate of this stuff. That's why there's a minus sign there and there's not one there. On the other hand, when I bring those constants 1 over IH bar out of this one, okay, it comes out as a positive IH bar in the denominator. Got to be careful about order here, right? Hamiltonian operator, just operator right there. And then it's Q Hamiltonian because I'm taking that derivative. The order is QH here. The order is HQ here. Okay, next step, I guess, I slapped that guy and I brought it right in there, preserving the order, but bringing it to the ket side of the integral. And of course, for about the third time today, I can do that because the operator H is Hermitian, right? All our operators in quantum mechanics, including the energy operator, are Hermitian. So I can bring it over there. And this guy right here, I guess, becomes the expectation value of the derivative of the operator with respect to time. And this thing is, of course, just 1, psi star psi. We're assuming our wave functions are normalized, our eigenfunctions are normalized. All right, so I bring that guy over to there, and I look, and this is HQ, negative sign, QH. Sure looks like that's going to be a commutator. And then I brought these two guys, the psi star psi and the psi star psi, together, put them in one term where I subtracted the two, brought the constant outside. Oh yeah, you notice this one's negative where it used to be positive here. Notice I slapped the I from the denominator to the numerator. And by doing that, I multiply by minus I over minus I, which causes that to happen. That's why it's positive IH bar, and this one's subtracted, okay? And so you can see right away that becomes the commutator of the two, and that term just becomes the expectation value, the rate of change of Q. Now, generally, in fact, can you think of an operator that has an explicit function of time, not just of X, right? Like we say, X operator is equal to X. Remember, this is a position now. There's no operator that on this side right over here, minus I H bar ddx, is explicitly a function of time. And so if it's not explicitly a function of time, if the operator is not an explicit function of time, its derivative with respect to time is, any case I've ever studied in my physics life, that term has always been 0, okay? And so if this term is 0 because operators don't explicitly depend on time, and the commutator of the Hamiltonian, the energy operator, and any other operator happens to be equal to 0, then you can see that the rate of change of the expectation value of that operator is 0. And so the expectation value of the operator is a constant. We say that quantity then would be conserved. That's what we mean when we say a quantity doesn't change, like energy, momentum, charge, mass, all those sorts of things. So what about energy and time now? In the couple seconds I have left, I want to follow up from that idea that the rate of change of the expectation value is I over H bar times the commutator, the expectation value of the commutator, the Hamiltonian with some other operator. And I want to apply that to our generalized uncertainty principle, that boxed equation I had earlier. And now we're going to say that A and B are, of course, the Hamiltonian and Q. And we said that's 1 over 2I. And so it'll be the commutator of H and Q then with the 1 over 2I. And we just said, I think, that this commutator, wrong way. No, cancel, discard, go back. Sorry, I went forward. Come on now. Don't quit on me. All right, and so open that back up. My apologies. And we had said on the previous slide that the commutator of H and Q is the derivative of the expectation value with those constants I over H bar. And so for that commutator right here, I substituted that guy right there. Okay. And so let's see, that means the I and the I kind of become -1, but I'm going to square them because you're squaring in the generalized uncertainty principle. And the rate of change of the expectation value is also squared. And so that tells me that taking the square root of both sides, the standard deviation of the energy times the standard deviation of some other parameter must be greater than or equal to, that should be H bar. And I guess that should be H bar, and that should be H bar too. I don't know why that got dropped. I would have swore it's H bar over here, I can see. That has to be greater than H bar over 2 times the rate of change of the expectation value. And I went with magnitude because it was square root here, and I took the square root of both sides. All right, compare that to the uncertainty principle for energy and time we know. Pretty clear if you're comparing these two things. Well, that's the comparison right there, right? The standard deviation in H, the Hamiltonian, the energy operator, we've always called that delta E. And so I guess that must mean that delta T here is the uncertainty in this thing Q divided by that guy, right? Because notice it's not there on this side. Okay, so delta T then has to be the uncertainty in this other parameter, this other measurable whose observable is Q, divided by the rate of change of that expectation value in time. Okay, so now you can see what I said at the very beginning of this segment where we're talking about energy and time. Delta T represents the amount of time it takes the expectation value of some operator to change by 1 standard deviation. The words I used at the start was to change substantially. Okay, substantially means the expectation value of Q has changed by exactly 1 standard deviation. And clearly delta T is going to depend on what observable Q you're looking at. Doesn't really matter. That's T by itself is not really relevant. It's what other observable besides energy you're looking at. But if delta E is small, then delta T has to be fairly big, and the rate of change of that other parameter's expectation value, it must be pretty slow, right? That is the significance of the energy time uncertainty principle. On the other hand, if an observable is it's supposed to be an observable, get rid of that right there. An observable changes rapidly, the uncertainty in the energy must be large. Okay, so if this other operator expectation value is changing rapidly, so that's a big number, delta T here is small, well then energy must be, the uncertainty in energy, delta E, the standard deviation in E, must be a big number. Okay, one final comment on this before I let you go, and Griffiths points this out. I think it's more his opinion. There are people, physicists, who'll say, hey, look, energy is conserved, but there's some variation in energy about that conserved energy. It could perhaps happen, but it can only happen for a short period of time. And that's an interpretation of this. And the author of our textbook, he doesn't agree with that. He would argue that there was nothing in anything I said here that said that energy wasn't conserved. But I think the way to interpret it correctly, Griffiths doesn't tell you how to correctly interpret it. I think what it tells you is, as a laboratory scientist, you may be confused by the measurements you're making, because the measurement you make may show that energy isn't conserved because of the energy time uncertainty principle. Nobody's saying that that means that energy isn't conserved, but only for a short period of time. Okay, we're just saying that in a laboratory you might be confused by the uncertainty principle when making a measurement. All right, that is my last slide. Would have been done a second ago if I hadn't screwed that up for you. Any questions before I call it a day here? All right, that being said, it's time to quit. The tutorial that's associated with what we talked about today is on Canvas. Download it, take a look at it, and it is due Friday. Again, I'll be at office hours around 1 o'clock here, about 35 minutes. Any questions you've got on either the tutorial from last Friday or what we talked about today, I'll be there to answer questions. Y'all have a great day. Stay safe, stay healthy, and we'll keep pushing through this stuff. Last chance for questions. All right, then we're done. Have a good one. And look at those boxes just start disappearing. There's one. Now they're back awake. They're awake. You're gone. Okay. See you later.